The basics that we're going to cover anyway in this is resonance, common antenna designs, antenna gain, and antenna length and loading. First one is resonance. So the best way for me to kind of visualize resonance is you can think of it almost like a sound wave. You know, you've seen a S wave or something of that nature. An antenna is tuned to a particular frequency in which that it resonates. So let's say you have a radio that's on 146.52, 146.52. You want an antenna that is going to resonate in that frequency band. If your antenna is too short or too long, it's not going to resonate properly and it will be an inefficient antenna. Right, not that it won't work, but it's not going to be as efficient. Antennas radiate most effectively when the AC fed into the antenna is at or near its natural resonant frequency. So, yep, like we just said. Much like a swing. A finite time is required for the swing to complete a cycle depending on its length. Length determines the resonant frequency. A finite time is required for AC to complete a cycle across the antenna depending on its length. So lower versus higher. Length determines resonant frequency. Longer is a lower frequency, whereas a shorter antenna is a higher frequency. So if you ever looked on the back of a cop car or an ambulance or something like that, years ago they used to have the quarter inch. We call them a quarter-inch whip. They're 19 inches, I believe they are, for VHF. Nowadays, the new antennas for the 800 megahertz system are about that big.
That directly corresponds to the what is it? It's not the frequency; it's the wavelength.
Yes. Yep. Exactly. Yep. So the larger the antenna, the lower the frequency. The smaller the antenna, the higher the frequency. So. Yes. Yep. So like what Larry has here, so this is a HF antenna. What do you got this for right now? Is this
10 meters?
10 meters?
It goes from 40 to 10.
Yep. Okay. So his antenna is currently set up for 10 meters, which is 28 megahertz roughly. So what you're seeing here, obviously this part of the antenna is already quite large, but even for the 10 meter band, this still isn't large enough. So this coil is effectively making this antenna longer and therefore resonant within that frequency band. Transmitter frequency is the reinforcing push. Yep, so when the frequency is matched to the natural cycle time, the system is at resonance.
It's like being in tune with an instrument.
Yep, exactly. So the half-wave dipole antenna is constructed of two conductors. One's attached to the RF conducting side of the transmission line, and one is attached to the ground side. So with any coaxial cable, you're going to see there's always a inner element, and then there's usually a foam insulator, and then you've got an outer shield. It's usually aluminum braid or something like that. So what they're talking about here is one side of the dipole is going to attach to that center conductor, and the other side is going to attach to that outer shield. The total length of the antenna is approximately half wavelength of the operating frequency. So one of the best antennas I've ever had for HF was my half-wave 80-meter dipole, which was, I can't do the math in my head, but like 132 feet long, and it was massive. It stretched it out across the trees, and unfortunately the wind took it down, but it is a half wavelength. So if you double that, you get the wavelength of the 80 meter band, which is, yeah, I can't do that math either. I'm terrible. But whatever 132 feet is, that is half of what the 80 meter band is. Obviously, it's not very realistic to make a full wave antenna. You'd be talking about hundreds and hundreds of feet worth of antenna. So a half wave is resonant in that and will work just as well. Yes, yep. Quarter waves, half waves, they all have different takeoff angles. So when you're talking, we're talking about dipoles in the horizontal right now, so takeoff angle is relevant, but not quite as much as it is when you get to vertically polarized antennas for like VHF, UHF. So a quarter wave tends to focus more radiation towards the sky, whereas like a 5/8 wave is more focused towards the horizon. So when like selecting a mobile antenna for your car, you know, if you can get a 5/8 wave antenna, it's usually a little bit better than a quarter wave is.
So with the horizontal, is that because it basically resonates in a circle, so you're kind of shooting at all angles?
What is really the logic behind? Is there? Okay, yeah. I haven't gone through these slides, so then that's my bad. So okay, yep. So just like I was talking about there with the center conductor and the outer shield, you can kind of see how that's attached. The resonant frequency of a dipole antenna is increased by shortening it. So like we said, the smaller the antenna, the higher the frequency. So like when I'm building an antenna, you know, if an 80 meter dipole is 132 feet or whatever it is, I'll usually cut my wire to, let's say, 135 feet. You put it up, you can kind of check to see how resonant it is, and then it gives you some to trim off to get it down to where you want it to be.
And just a hint too, you don't have to cut it physically, you can just wrap it on itself. And even though it's 3 feet too long because you've wrapped it on itself electrically, it thinks it's the right length. So if you ever need to make it longer, you've got some extra cable.
And I think they do that with, is it fan dipoles? There's some I don't remember now, but there's some dipole where you know, you'll mark it for 80, 40, 20, and you can roll it up to that mark and have, you know, and then you can roll it back out for the lower frequencies. Yep, exactly. Because, and this is getting ahead of things, but when you get into HF, you'll find that certain frequencies work better for certain times of day. So like 20 meters during the day, fantastic. At night, it usually goes away. You switch down to 40 or 75 or 80 meters. So you'll want to have your short antenna for the daytime, and then you want to extend it out in the evening.
Yeah, we talked about propagation last session.
Okay,
So.
okay, very good. Half-wave dipole antenna radiates the strongest signal broadside to the antenna. Yeah. Yep. So, and I think that kind of ties in why we do it horizontally for high frequency stuff, is because with HF, you're wanting to use the ionosphere to bounce your signal around. So having it straight up and shooting into the ionosphere is great. Whereas if we turn this 90 degrees, you can see how that pattern is left and right for VHF, UHF, close-in stuff. They do use verticals for HF. You know, obviously this is a vertical right here. I've done some great things with a Hustler 5BTV. I've talked to Australia and South Africa with a vertical. So, you know, to each their own on to what you choose.
The thing about UHF and VHF frequencies, because the wavelengths are shorter, they tend to go right through the ionosphere.
Yep.
So the longer wavelengths, relatively longer,
Right.
That we're talking about, tend to bounce off, where the shorter ones go right on through. So that's why we say line of sight coverage. Because
Right.
you can go up in the sky, it gets there, it just keeps on going, and it doesn't get reflected back.
All of our signals are out there chasing down chasing the Voyager down, or, you know. How can a half-wave dipole be configured? So Couple different options here. Flat top, I've never seen it referred to as a flat top. That's interesting. That is I would say the primary means of a dipole typically. They're usually right horizontal with the ground. Inverted V and a sloper. So those are all pretty self-explanatory. I'm hoping the next slide kind of discusses what each one does. The dipole feed line should depart the antenna at a 90-degree angle or near the center of the internal angle of an inverted V configuration.
Yeah. What was it? There's a diagram in the Ranger handbook about making a V antenna out of it.
Yes. So a lot of people just getting into this kind of are looking for the, I'm going to call the long short range communications, which is like the next town over or halfway downstate or something along those lines. That is, and I'm sure that's going to be in here or it may have been already covered, is what we call NVIS or near vertical incidence skywave. Wow, pulled that one out. NVIS is a means of trying to get your signal as straight up as possible so it comes straight back down as possible. So you're trying to keep your range out to like 300, 400, 500 miles at most. With an antenna that's not set up for NVIS, you're talking 1,000 miles, 2,000 miles worldwide at that point. For NVIS, just wanting to just cover like a state, you get that in the configuration, so it only does 300, 400 miles. And the way that that's done is typically with something like an inverted V or these sloper configurations, and then typically they're very close to the ground.
Yeah, the one in the book, I think, I'm assuming it was designed to shoot back towards a specific spot. So
Yep.
it was a V kind of pointed upwards.
Sure.
So
Yep.
It was, and what was it? You're supposed to shoot the compass like that's the direction back to base or whatever.
Yep. So back to that I like to think of it as a donut configuration. If you're trying to put if you're wanting to put your signal in one direction, you could effectively figure out which way that antenna is going to radiate the best, and then point it in whatever direction that is. Yes, exactly. Yep. And to be honest, the best NVIS antenna I've ever had is an 80-meter dipole hung very low, like 35 feet. It just works so much. It works so well.
The curious thing about a regular dipole, because it bounces off the ionosphere, it's difficult to talk to people relatively close. So the NVIS that Adam was talking about, the 200 or 300 miles, you can't talk to somebody 200 or 300 miles away. If I'm doing 20 or 40 meters and they're in Michigan, I have a really hard time hearing them. Even in Wisconsin, just because of, think of billiard balls where they're bouncing off the side, you hit the ionosphere and it sort of goes over Michigan down to Florida. So you need something to be able to talk close by. It's just interesting that you'd think someone closer would hear better, but in some cases.
If you ever get into contesting, you'll be contesting or you'll hear a station, let's say, I always get the ones in like Pennsylvania or Vermont, states out that way, just the way propagation's been lately. And you'll hear a station super loud, just pegging the meter, they're rock solid into you, and they're talking to somebody from Michigan. And you can't hear the other side of the conversation. You're just listening, and they go, and you'll hear a call sign from Michigan, and you'll go, oh, okay, well, they're hearing Michigan, so I guess I can check in, but you never hear that other guy. He's too close to you.
You're inside the mark.
Exactly, yep. So that's a good kind of visualization of, how the signal propagates across the wire. There's there's electrons and the flow and all that.
It gets a little theory.
It does, yeah.
And unless there's a question number work locker lines up, so.
Right, exactly.
There's not a question, I don't think there's a
Right.
question on the exam about this, so. I mean, it's good to know it, but there's not usually if there's a number there, it signifies that there's a question on that.
Yeah, okay.
I don't think there's a question on this.
I don't, of course, they've updated the technician since I took it, but I don't recall, needing to know how the voltage oscillates on a dipole wire. That wasn't, I mean, you eventually you get to the point where you have to learn it because you're working on this stuff, but it's not part of the, it's not,
AC, so.
yeah. Yep. Just reading through that real quick to make sure there's nothing. Yeah. What are common antenna designs for ham radio? So here we go, talking about the quarter wave vertical antenna. It is constructed of one conductor attached to the RF conducting side and a ground plane attached to the ground side. So quarter wave, you can think of one as like being on a car. Your ground conductor is going to the ground plane, which is like the roof of the car. That's your metal ground plane. On a HF vertical, you see all the yellow wires that Larry has coming off of his antenna here? That is the ground plane. So it's effectively it's not like a metal field, you know what I mean? Obviously the roof of a car is a metal, field there, but these are effectively doing the same thing. It's giving the antenna a ground plane and helping with the propagation. Right, exactly. That's what I was looking for.
Kind of like making like an electromagnetic field that it can bounce off of.
Yep, a ground plane is constructed of a conductive material oriented perpendicular to the vertical antenna element at its base. Yep, the ground plane may be considered an RF mirror that provides a virtual quarter wave ground element, much like the ground side of a dipole antenna.
I was just going to mention on UHF, VHF.
Yep.
Fingers looking down.
Yep, so most dual band base station, VHF, UHF base station antennas will have this ground plane configuration. These are effectively the same thing as Larry's yellow wires here, but again, it's all relative to the frequency. So when you have a shorter antenna because you're at a higher frequency, you also have a shorter ground plane. Okay. So same thing goes with antennas on your car. Let's say you have a VHF, UHF antenna on your car. You need roughly 19 inches of ground plane. So you can mount that antenna, off to the side a little bit, maybe towards the back. As long as you've got 19 inches all the way around it, you're good. HF antennas, on the other hand, if you tried to put, like a 10 meter or, 20 meter, something that's reasonable, you would need, the entire, you'd have to put it right in the center, basically, to give yourself more ground plane.
That's why you always see the trucks with the big old antenna in the center of it?
Yep, exactly. Yep. And that's done for a purpose. You need as much ground plane around that antenna as possible. And then you get into screwdriver antennas mounted on Reese hitches, and then you've got ground straps going to the frame of the body. It's just... Yep, exactly. It's like this is reading my mind. In fact, we'll open up the whole slide there. How is antenna length determined? The length of a half-wave dipole antenna may be approximated by this calculation. So I think that's in the test, isn't it? Yeah. I'm pretty sure those are in the test. Oh, I see what you're saying by numbers here. Yes. So, yeah, that's indicating that that's in the test. Right. You may not get it, but you also might. So that's one area where I struggled because I'm terrible with formulas and calculations and stuff like that.
The easy way to do that is in high school we used to have a cheer, 2, 4, 6, 8. Who do you appreciate? Well, it's 4, 6, 8.
Yeah.
Divide it by your frequency, and there's your feet, and then a quarter wave is half of that, 234.
Yep.
So 468, 234. That's
There
all
you go.
gotta remember, divided by the frequency.
That's a good tip. Even I'm learning something.
As I say, if you're doing it in meters, it's divided by 300.
Oh, yeah. So
So
that's,
they're doing it in
That's what we
feet.
were calculating.
Yeah.
So, yeah, like Adam said, I think the rule has changed. When I took it 2 years ago, everything was in meters still.
Okay.
Yeah,
Yep.
they talked about meters a little while ago, so they may have added this.
Yeah.
Well, kind of like it's saying here, first convert 6 meters to 50 megahertz, you know.
Right.
So-
you gotta do 300.
Right, exactly. So definitely that would be one area, because I think that comes up a couple of times in the question pool.
Yeah, well, in the bands are major distributors, but it's real rough. I mean, some of them are off. I mean, you get to the 80-meter band, there's even a 75-meter band.
Well, that's just it. Most general license class people never actually use the 80-meter band. They're always using the 75-meter band. You know, the 80-meter band is where you get down into CW and digital and stuff like that. So,
If you just remember 468 and 234, you know, the half wave is bigger, so it has bigger numbers. The quarter wave is smaller, it has a smaller set of numbers.
Yep.
The quarter wave is half of a half wave, so it's half of that 468, which is 234.
yep.
So that's all you, and you're golden for the test.
Oh, there we go. So this is another type of antenna. It's called the Yagi, however you want to pronounce it. Yeah, absolutely.
We're going to talk about this satellite, so it is a Yagi, so we
Yep.
can figure it out. So I felt that Steve Brewer. So it's actually two antennas. It's a UHF and VHF. I'm going to kind of leave it at that because I'll talk more about it in the satellite piece. But anyway, so that's a Yagi. The longer ones are the VHF.
So I'm trying to see what it's actually saying here, but so what these do, I don't know if you've touched on gain yet. I think gain is in this later on, but you have loss and gain in all of this. So your loss is your feed line, you know, your coax going up to the antenna, antenna connectors, anything like that is all loss. It's where, let's say you have a 50-watt radio and you're trying to put 50 watts to the antenna. That coax is going to lose a certain amount of dB, decibels. You know, it's usually 0.3 for a connector or something like that. So by the time the signal makes, or the transmission makes it from the radio to the antenna, you're maybe doing 48 watts or something like that. So that's your loss. You can also get gain in the form of a better antenna. This, what's a 3-element Yagi? Like, it would be like 3 dBi, right?
Yeah, I would think so. It's measured against isotropic dipole.
Right.
1.2 dB or something.
For the sake of the conversation, we'll call it 3 dB. So a Yagi antenna is 3 dB of gain over a standard dipole. So it's increasing your power there 3 times, which...
And just to comment on that, so you really never increase your power. If you got 50 watts, you always have 50
Right.
watts with what rather 10.
Right.
What it does is it focuses what power you've got in a certain direction.
Yep.
It's like a flashlight. If you don't have a reflector on a flashlight, it just sort of goes all over. So as you put it in like a headlight and focus it, you know, it gets really bright, but only in one spot. So there's no more light there. It's just that we
Right.
took it and threw it in a direction and the radio wave.
There is, and one of these days in this class, or maybe we'll do it in the Hammond a day, I will pull up a program called Radio Mobile Online. You ever mess with that? So Radio Mobile Online is a propagation calculation piece of software for determining how far, like a repeater the range will be on it. And when you're doing those calculations, let's say you have an antenna that is 6 dB gain and you're doing 100 watts, there is effective radiated power, ERP. So your ERP is the combination of power and gain, and it does come out, it actually does spit out a number to you like your ERP, if you're running 100 watts, your ERP is 250 watts or something like that. So while you're never going up in power, say from your radio, what the effective radiated power is from the antenna can be increased. Just like that with focusing it into a certain pattern. And that's what an antenna like a Yagi does. So you've got your dipole. So your dipole is this center element. See where he's got the coax coming to, and then you still have your two elements. You've got your side going to the center conductor, and you've got your ground side.
It's separated in the pipe, you can't see it.
Yep.
But they're not, it looks like they're connected, but they're not.
Right. So you have your dipole here. You've got one element that's longer. This is reflecting anything that's coming off this antenna this way gets reflected back. And then this element, because it's shorter, is driving it forward. So this antenna is taking anything lost back this way and also doubling it up this way and pushing it all in one direction. This is a directional antenna. So if you were to transmit or receive from this way, you'd hear great here, but if you had a station over here, you wouldn't hear them at all. You really wouldn't hear them at all. Sometimes you can, and then as you swing around, you would pick up this station and lose that one. Quads are, as far as I'm concerned, they're glorified Yagis. At least that's my interpretation of them. I've never tried to use a quad. It's way too much math for my brain, and I don't see much benefit from it. But they are there. They do exist. And same thing, they have a reflector, a driven element, a director, and so on and so forth. And then you have a dish, which is, again, just focusing that energy from either from the received signal or focusing it, transmitting it out. Believe it or not, you will sometimes get into dishes if you get into the microwave spectrum. So with the technician license, you're restricted on some HF stuff, but you're pretty much wide open on anything above VHF, UHF. You can get into 900 meg, you can get into 1.2 gigahertz, and beyond from there. When you start getting into like 1.2 gigahertz, that is, you're switching over to dishes at that point. That's the most effective way to transmit and receive those signals is with a dish or something of that nature. What is antenna gain? The antenna gain is increase in signal strength in a specific direction compared to a reference antenna. So same thing, like I just showed you with Larry's Yagi, you can see where the driven element is, the reflector, and then the directors above it. Directional antenna produces gain in one direction by concentrating signals. Isotropic theoretical antenna radiates equally in all spherical directions. Equivalent power input is isotropic directional antenna. Isotropic's losing me there. That's a little bit above my pay grade even. I don't know.
It's just a theoretical antenna in a perfect situation that never exists.
Oh, okay. Yeah.
Without any gain whatsoever. So a dipole would be an isotropic antenna.
Right, okay.
With nothing else.
Yep. So everything is in yeah. Whenever you're talking about gain, it's always in reference to a dipole. Let's see what the next slide says before I go jumping ahead of it again. Yep, we talked about that. And that's a good infographic on it. Maybe it's good.
You can see how that back reflector is catching it and like making that air pocket.
Yeah.
And then putting it forward.
If you go back to the previous slide, you've got the little map, or one more. See the little map on the, more of the center of the screen?
Yeah, the one for the
Yeah.
directional antenna.
Yeah.
So it's showing you the radiation pattern.
Yes, yep. You're right, and I missed that. So,
You're getting twice as much in one direction.
you know, it's showing you like this would be your radiated element, and then this would be your reflected element here, and then your directors. And you can see you do get a little bit back here, but it's not anything in comparison to what's going out that direction. What is different about mobile antennas? They're on cars. Groundbreaking stuff here. Cars, oh, and cars that are mobile too.
The
Jeez.
snark is strong with this slide.
So if you have a car and a trailer, are you mobile?
Yes.
Okay, just making sure.
Okay, it's wanting to make noises at me here. Oh, it just wanted the car to slide. I'm just wanting to get the full slide there, so I keep getting ahead of the slide. The type of antenna loading is electrically lengthening by inserting inductors in radiating elements. So again, we've already talked about this briefly. An inductor, a coil of wire that's attached to the antenna, just like we have here. So that's what this white piece of pipe is here, and then you can see the coil of wire around it. Using loading, a mobile antenna for HF bands can be made small enough for practical mounting on a vehicle. Mobile antennas are often mounted in the center of the vehicle roof, which we talked about, as it provides a broad ground plane and results in the most uniform radiation pattern. For your VHF, UHF mobile service, an advantage of a 5/8 wavelength whip antenna is that it has more gain than a quarter wave wavelength antenna, usually providing improved coverage. Again, I apparently am just reading the mind of this slide. Yes, it is. Yep. And even apart from that, when you get down to it and you start mounting radios in your cars and things like that, always try and go with a 5/8 wave. I mean, quarter waves are fine. They work for, they work for public safety and commercial because they have the infrastructure around that. They're not worried about how efficient their antenna is because they've got 6 repeaters in a 20-mile range and they're good. They don't have to worry about it. Hams, us on the other hand, we're limited to how many repeaters that we can put up. It's exactly. So they're not, every 15 miles and they're not all, so yes, you're always going to want to have the best chance possible, and you're going to find that usually in a 5/8 wave. Normally what you're going to see is a stacked collinear 5/8 wave. They are ridiculously long antennas, but they work extremely well. They are 5/8 waves stacked on top of each other over and over again in phase with each other. And they provide, like my Diamond, I forget what model it is, but that thing stands taller than I am. And it's just VHF, UHF, that's all it is. And it's, I think it's 11 dBi on UHF and 8 dBi on VHF. It is holy cow gain, but it's massive. So trying to find a higher gain, 5/8 wave antenna for your vehicle is you're gonna be a lot happier with it. You might hit a couple trees, you might have to do something when you're pulling in the garage, but performance-wise, it's going to be far better than a quarter wave. What's a dummy load? A dummy load's primary purpose is to prevent transmitting signals over the air when making tests. A dummy load consists of a non-inductive resistor mounted on a heat sink. Takes place of an antenna for test purposes, keeps test signals from interfering with others, does not radiate a signal, not much. Basically a big 50 ohm resistor. So places that a dummy load is wanted, repeater building. You know, we do quite a bit of repeaters. We have 1, 2, 3, 4, 5, 6. We have 6 repeaters just in our little neck of the woods here that we take care of. When you're building out a repeater, let's say you're building it on your desk at home on the bench, you don't necessarily want to be broadcasting 100 watts of repeater power from your garage or your basement or wherever it is. You want it to be at the tower site, not while you're just tinkering on things. Putting it on a dummy load so you can do your testing is the best option for that. You can set it, you can put a repeater, or even if you're testing a radio, if you're wanting to find out if your mobile's working or not working, you can set it on a table, put it into a dummy load, and you'll still be able to use like a handheld into it from close by. That's why it says it radiates some. It will do, in the same room, or maybe even in the building, but it's not going to be blowing out everybody down the streets, TVs and stuff like that if you're doing like, a 250 watt repeater or something of that nature. Obviously, you have to have a dummy load that can handle that power. Some are only rated for 5 watts for a handheld, some are rated 25 watts, and then you get these monster ones that are about the size of this table that are, 1,000 watt capable or kilowatt. But having a good, I would say good 100 watt dummy load for your mobiles and things like that would definitely be a great thing to have. It looks like those are both on the test at some point or in the pool. To prevent transmitting signals over the air when making tests, and it consists of a non-inductive resistor mounted on a heat sink. And they do get very warm. Yep. Was that the beginning of the slide, Larry?
It cycles back around the end.
Yeah, you're done.
I'm done. Okay. Oh, there's 3 pieces to it. Okay. Oh, yeah. All right. So we're getting into SWR.
I've got an SWR analyzer there, or antenna, whichever you want.
Just trying to figure out. I don't like how it takes away parts. I just want to get the whole slide there so we can talk about it, but that's okay. SWR, standing wave ratio, a ratio describing the relative magnitudes of forward and reflected voltages in an antenna transmission line. So again, we're talking about, you want to try and get close to 50 watts to your antenna. If you have an antenna that's not resonant, like we talked about earlier, let's say you're trying to do VHF 146 megahertz and you're using an antenna that's tuned or resonant for we'll say 460 megahertz, the commercial UHF business band. It's not resonant at that frequency, so it's not going to have a proper or a good SWR. So you're trying to put 50 watts into it, it's all subjective. You may get 10 or 5 or 8 or whatever the number is. You'll start seeing reflected power. So some of that power is coming back down the coax because it's not effective enough to radiate it out of the antenna, and you don't want that because it will cause damage to your radios. And that's where SWR comes in. You get an SWR meter, you test your antenna. If your antenna's reading, a high SWR, that's going to create a lot of problems for your radio. Reflections in an antenna feed line result in positions of impedance mismatch. And so that's just kind of showing you where the, forward signal versus reflected signal. Difference in voltage when signals are instantaneously out of phase. Yes. SWR may be computed using measures of forward and reflected power.
I think that's on the test, it's a pretty heavy-duty formula, so.
Yeah. Yeah, I don't see it on there. And I don't know if they're going to, I'm sure they're going to, I'm waiting for them to say like 1-to-1. I haven't seen that yet. SWR is a measure of how well a load is matched to a transmission line. Load is the radiating antenna. Transmission line is the coax. And matched means the impedance match from the two parts there, from the antenna and the coax. Impedance is the opposition to AC current flow in units of ohms. I remember that on the test. That's a big one there. I don't know if you've ever seen an Ohm's law, the circle, the volts, ohms, resistance, things of that nature. I'm sure it's probably in the book. It's something that I would take a look at, study it. If it's not in the book, try and find one online. And then also do a Ohm's law calculator. So that's, volts times resistance equals power. Power times volts equals resistance. I can't remember exactly, but that is a formula that you're going to want to have all throughout for sure. And I know they hit it hard on the test. It comes up several times in the pool.
It's a little goofy. They don't use the first letter of the word. So
Yes.
volts would be V, but it's really E.
Yep.
And I is current, and R is resistance. So you
Yep.
just got to memorize.
Yep.
E equals IR. You just got to memorize. And I don't know if that's in this slide deck or not.
We'll see.
I'm sure it's in the book.
Optimally, the entire transmitter feed line antenna system will have the same characteristic impedance to avoid reflections. Well, I'm here to tell you, no antenna system's ever perfect. You can get darn close, but not quite.
You can tweak it too, right?
Yeah. Yep. An SWR ratio will be equivalent to the ratio of the impedance mismatch. Example, a 50 ohm coaxial feed line connected to a 10 ohm antenna feed point connector. 50 ohms divided by 10 ohms, 5 divided by 1, so you got 5 to 1 SWR. So there's the ratio number I was looking for. You want to be as close to 1 to 1 as possible. You're never going to really see 1 to 1, at least I never have in all my years of doing this. 1 to 1.2, 1 to 1.5, those are pretty acceptable. Most radios are still happy even if you get to like 1 to 1.8. So, yep, Larry's antenna right now is running 1.26 to 1.
So I brought an antenna tuner. I think we'll talk about that being in the slides to tweak it. But I didn't even use it because I got it, the coil adjusted so well.
Yep.
So anything under 2 is pretty good.
Yeah,
If you're
anything under 2.
1.5, you're really good.
Yep, exactly.
It just doesn't do you much good.
And some radios, if you've got a more modern radio, if it sees an SWR of, let's say, 1.3 to 1, or of 3 to 1, it will actually shut the radio down and won't let you transmit because it's protecting itself. This here is saying 4 to 1 is an impedance mismatch. I'm here to tell you, I guess I would study that number for the test, but I don't like anything that's, I don't like 2.5 or more, realistically. If I'm installing a new antenna, installing a repeater, anything of that nature, if I'm seeing 2.5 to 1 or above, I'm not happy with it. There's something wrong. The test is telling you 4 to 1. That's a high SWR.
This is a kind of a portable radio. It's one I use in the parks. I've got a bigger HF radio, and it's got a antenna tuner built in. So this one doesn't, so that's why I brought this separate tuner. But most built-in tuners will do 3 to 1 is the highest SWR will cure. So if you're 4 to 1 and you've got a tuner in your radio, it won't even tune that.
Right.
So I had them try, try and get your antenna to 2.5.
Yeah.
I was 1.2 or 1.3. I mean, that's pretty good.
Yeah, 1.2, I mean, even 1.5. 1.5 is acceptable.
Probably don't want to do it to hear the audio difference.
Right.
1.2 or
Exactly. Yep. And that's just it. This higher SWR, it's twofold. Not only is it damage to the radio, but it's also restricting your signal, both received and transmit. So if you're 1.3, 1.4, 1.5, I'm sorry, I keep doing that. If you're 2, 3, 4, 5 to 1 SWR, those really high numbers, your receive is going to be severely impacted, and your transmit is going to be severely impacted. If you're 5 to 1 SWR, let's say you're doing 50 watts out of the radio, you're doing basically 25 watts to the antenna, 25 right back to the radio. So at 50 watts, if you could reach that repeater that was 30 miles away, and all of a sudden you have a 5 to 1 mismatch, you're not going to be making it into that repeater anymore. So not only is it damaging to the radio, but it's also damaging to your signal. So 50 ohm coaxial feed line connected to a 75 ohm antenna feed point connector, 1.5 to 1 SWR. Antennas aren't 75 ohm connectors, are they? Yeah, that's weird that they would even say that in here. I've seen a 75 ohm jumper for microwave equipment. Well, most 75 ohm cable is for like cable TV, like your Type F cabling for your Charter, your Dish, or whatever. Right, you don't want to use that for ham radio because it's 75 ohm resistance cable. That, and we kind of just a backstory to all the the stuff that you can get involved in as we're out building repeaters. We recently moved a couple of our repeaters from up in Stutzmanville down to Kraus Road, just south of Petoskey here. We were taking over one of CCE's old VHF sites. And in that, we were removing a bunch of equipment to take back to them, and in some of that was these really nice short jumpers for connecting to various duplexers, things like that. These short jumpers, they were really nice. So we went to go put some of these jumpers on between some parts of the repeater, and all of a sudden the repeater started going into an SWR alarm, just having a fit. It did not like it. Come to find out, those jumpers were 75 ohm jumpers because they work better for the microwave system that used to be there. That's what they were connected to. They were connected to the microwave transmitters and receivers. We didn't know they were 75 ohm. They just looked like regular run-of-the-mill jumpers. Pulled them off, tested them with a meter. Sure enough, 75 ohms. Put some other jumpers on. Perfect SWR. All the alarms went away. So I'm kind of questioning why they're throwing 75 ohm in here. Everything's supposed to be 50 ohm.
I think it's just an example of this.
Yeah, well, there's connected to a 75 ohm antenna feed point connector. So, yeah. Most of your jumpers, your coax, your fittings, your antenna points, they're all going to be 50 ohm. Yeah, 2 to 1 or less are considered good. I wouldn't be, if let's say you install a mobile in your car and all of a sudden one day you're just like, it's not quite working as well, and you check the SWR and it's 2 to 1. I don't think I'd drop what I was doing to work on it. You can get by for a little while, but I wouldn't call that good. Somewhere along the line, something, whether it's the connector on the roof has gotten corroded, or something of that nature. They're telling you 2 to 1 is good. It's okay, but I would still, whatever you got to do to try and get it down. Yeah, 50 ohm feed line to a 50 ohm antenna feed point should be a 1-to-1 SWR. 1 to 1.5, that's probably what you'll see. A perfect impedance match between the antenna and the feed line. Again, it's never perfect. What does an antenna tuner do? Just what Larry had here just a second ago. The major function of an antenna tuner, or antenna coupler, sometimes they are called that, and it may show up that way on the test too, I don't remember, is that it matches the antenna's system impedance to the transceiver's output impedance. So, let's see, it'll probably go right into it. An antenna tuner is usually a separate station component placed between a transceiver and an antenna in the feed line. An antenna tuner presents a desired 50 ohms impedance to the transceiver even if the true SWR of the antenna system is mismatched, thereby avoiding the power reduction and keeping the transceiver happy. The actual SWR of the feed line antenna system is not changed by the antenna tuner. So, Larry, you've got one here. Yours is a manual. Some of the ones, like I have an automatic antenna tuner. You want to go over that a little bit? I know how they work, but I don't know how to get the...
You don't need to know too much about it, but tuning an antenna involves both capacitance and inductance. So there are 2 variable capacitors in here, and it's those, a variable capacitor are those metal things that just, I don't have a picture of one.
Yeah, I know. I know what you're talking about.
A stack of wafers, and it varies. It's tunable. These turn, and they vary the capacitance. And this is an inductor. And I'm not a very good explainer.
Yeah, I'm like struggling to really.
But it's got a coil of wire in it, well, kind of like that.
Yep.
And you have different points. I mean, this is a continuous wire. It looks like a solid, but it's actually separated. And there's a. I'm not going to move it now because I'm going to tune it. We're going to use it in a minute. But this thing slides up and down, so it uses more or less a part of that coil. And using that combination of capacitance and inductance, it allows you to lower that SWR. Now, it doesn't improve the efficiency per se of the antenna because you can take a dummy load that Adam was talking about, looks like a can of paint or resistant, and you can get 1-to-1 SWR. Perfect. But you have no signal.
Right.
Because it's not an efficient antenna. So
exactly.
It's not all about SWR. Is why you want to try and get your antenna as resident as you can, and then you tweak it with an antenna tuner. I mean, that's for a technician license. That's probably
I would say that's probably more than enough. But what it's doing is, let's say you have a dipole for HF and it's cut to 135 feet and it's got 2.5 to 1 SWR. It's just a little bit too long or a little bit too short. It's just not quite right. Obviously, at those large scale antenna lengths, you're not going to run up and change something every time you change the band or whatnot. You can put an antenna tuner in place that will take that, let's say it's 75 ohms at the antenna and the radio's looking for 50, and it will make the radio see 50 ohms to the antenna, basically. It's basically fooling the radio saying, hey, here's your proper impedance, give me all the power you got, is the kind of long and short of it. Yep, as close to as possible. And most of them, like I've got an automatic antenna tuner, and it's got like an LCD bar that goes across. And as it's tuning, you'll watch the SWR. It'll be like 5 to 1, and you'll watch, and you can hear these things. They're clicking inside. They're changing that inductance and capacitance. And as it's changing, you can actually watch the SWR drop. And it'll go down to like 1.2 to 1, and then it'll say, hey, I'm all set. You can go ahead and transmit now.
So there's your 2 questions.
Yep. Yeah, I wouldn't worry about the formula. Google's a wonderful thing when you're doing this kind of stuff. So an SWR meter or an RF power meter should be installed in the feed line between the transmitter and the antenna. So, I mean, there's really nowhere else to install it, so I don't know why they hammered that home, but I mean, it's not like you're going to set it off to the right side of the radio and go, oh, that's good enough. Right. Well, that and they're telling you to install it, that should be worded differently. Anytime you do a new installation or setup, or you're trying a new antenna, new radio, new anything. So whenever anything's changed, you should always be checking it with an SWR meter first off, because you don't know if a piece of coax got nicked and the connector's not quite right now, or even if it's a new antenna right out of the box. They can be bad sometimes. What it's asking you to do is anytime you're starting with something else different, throw an SWR meter in line, make sure your SWR is good. Using the term installed means that it's there 24/7, and that's extra loss that you just don't want. So
Mike was right, I'll use it more for HF, but just a reminder, technicians can use HF.
yes,
So if you do Morse code, you've got lots of bands you can use, but only Morse code. But if you want to do phone, which we call phone as voice, or data, which we're going to see, you can use the 10-meter band,
Yep.
which is HF. Now, on the data, you have a real small segment, or I'm sorry, on the phone, there's a real small segment that you're allowed to use, but you can use the data part of it. So you can do HF, and that's
Yep.
why particularly I brought this, so we can do it on the technician. I mean, it's a 10-meter band, it's HF band, you do need to tune it,
Yep.
and it is available, will be available to you. So
and you guys are getting into it at the good time. When I got into it, we were at the bottom of the solar cycle, and the the higher bands, 10 meters, 12 meters, 15 meters, they stunk. They were terrible. And now we're climbing up into the top of a solar cycle here, and 10 meters is coming alive, and everybody's talking all over the world with it. So, yep. I think 2026 is the peak. Yep. So we're still riding the upswing on it. Yep. So you as a technician could jump right on 10 meters and be talking all the way around the world. I mean, right out of the gate. Yep. Yep. The other part of this, I guess, we've got another blue oval here. When selecting an accessory SWR meter, the frequency and power level at which the measurements will be made should be considered. So, right.
you got to make sure the meter can handle 1,000 watts, which most of them can.
Right.
You just have to be aware of it.
Yep. And your SWR can change based on power. I've seen that. I don't know what the formula is for it, but you can put 5 watts into an antenna and it might give you 1.2, 1.5, and then if you go and give it 250 watts, that impedance can change and you can all of a sudden have a 5-to-1 SWR. I don't know why. I've seen it. I can't explain the logic behind it, but I've personally seen it several times. Well, and then we're talking about watt meters. A directional watt meter can be used to determine SWR by taking separate power directional readings and using the formula to the left to compute SWR. I don't think, at least for a technician, unless maybe you got some in that stockpile of stuff you got, but normally you're not going to see this is a Bird watt meter. They're still in use today, but they are old school and they're also very expensive. Like a MFJ antenna analyzer that does SWR is going to be way cheaper than the Bird watt meter is. So will you come across it? Maybe, maybe not. But what they do is they have a slug inside them. So you have a slug that's tuned for a certain frequency, and you drop this slug inside, and then you can turn it left or right. And this way is forward power, this way is reflected power. And you can watch the meter, and then you flip it over and you key up again, and the meter comes up, and that's your reflected power. and you can use that to calculate your SWR. But, I mean, like an MFJ antenna tuner is what, like maybe $200, somewhere around there? I think the bird watt meters are, I want to say they're like $400 or $500, but I don't know. We don't really run into them. I mean, every once in a while you got somebody who's like, oh yeah, I got a bird watt meter and I got 17 slugs for it and I've had it since 1942, you know. Is there? Oh yeah, I do. Okay, I do see that now. Sorry about that. So a directional watt meter can be used to determine SWR. Yep, and it sounds like that, and that sounds like that's how they'll word it. Can a watt meter be used to determine SWR? Yes or no? And that's how they get you. But yes, it can be. I guess so. An antenna analyzer is used to determine if an antenna is resonant at the desired operating frequency. So, yep, there's the one I was just talking about. That's that MFJ. Yes, same thing.
But it does all sorts of other things too. It can measure repeats in your cable, tell if you have faults in your cable, opens or shorts.
Yep.
Length of the cable. You can do Smith charts. We don't do Smith charts. I don't think in the traditional.
No, I don't think so. The antenna analyzer connects directly to the antenna feed line and sends its own signals for SWR analysis. So it's taking the place of your transmitter. If you ever hook one up and you've got a handheld sitting beside you and it's like it's a Baofeng, one of the cheaper ones, you'll hear it as it sweeps the spectrum. You'll hear all of a sudden the radio will chirp for a second as it's sweeping through the spectrum. Well, there's an SWR curve plot. So some antenna analyzers will show you this plot, and it will have, a dip or a peak, depending on, some antennas are resonant in lots of places. So you can have a pretty flat line, and then you'll get some peaks in it where those high SWRs are, and then it'll smooth back out. This is showing you one that's very tuned for one specific frequency. It's very high SWR, and then it comes down for one spot, and then it goes way back up. Yes, so this drop here, so you've got your SWR over here, and these are your frequencies. So somewhere between 14.15 and 4, I'm going to say that's probably we'll call it 14.19. That is where your lowest SWR is at just under 1.2. But you can see and this is, to me, that's a little unrealistic, because if you're only going up a couple kilohertz and whatnot, and you're already shooting up to 3.0 to 1, that's pretty harsh. That antenna is very narrow band. And there's Larry's meter. And so you can see, like on his, and he can load it up and show you, but it's doing the exact same thing. It's showing you this kind of graph here of where your dip is on your SWR. You notice how it's nowhere near as sharp as this is? What is a coaxial cable? Coax cable is the most common feed line for amateur radio antenna systems because it is easy to use and requires few special installation considerations. That's one of the test parts right there. The other part of that is a reason to use shielded wire is to prevent coupling of unwanted signals to or from the wire. Coax feed lines can impose significant signal loss, especially at VHF, UHF, and higher frequencies. A benefit of low SWR is reduced signal loss. That's also a test point there. Since the power reflections in a coaxial feed line impose additional loss, it is important to keep SWR low in coax feed lines. Sources of loss in coaxial feed lines include high SWR, multiple connectors in the line, and water intrusion into the coaxial connections. Talking about connectors there. So, Larry's got his antennas. He's got a jumper here. So all of these are connectors, and then you've got jumpers, and sometimes you'll have to convert. Like, I don't know what this is that you got here, Larry, but I'm going to use it as a kind of a prop here. Oh, okay.
But there's an end connector on this.
So there's, so you've got your, your PL, or is that PL 259 and
SO 239.
yes. So these are your PL connectors, and then down here you've got a BNC connector. So you can have these adapters to change from different things. Each one of these is more loss. Some are less than others depending on how well they're built. You can get the super nice, what are they, Amphenol or something like that. They're real expensive, real high quality. They're less loss than the 99-cent bargain bin that you got from Amazon. You know what I mean? Yeah. Yeah, very well. I think it does. I think we're getting into connectors here in a second, but I'm just wanting to drive that home that, it's talking about where you can gain or lose loss. Connectors are a big one. What are the characteristics of coaxial cable? As the frequency of a signal in coaxial cable is increased, the loss increases. Power lost in a feed line is converted into heat. And this stuff does get hot. You get a real bad SWR and you're transmitting a lot of power, the stuff will get so warm that you can't touch it, whether it's your radio or the connectors or whatnot. Generally, electrical loss will be greater with narrower gauge coaxial cable, and loss will be less with larger diameter cable. So there's obviously thousands of manufacturers of coax cable, and they all have their specific models and brands and types. Like for VHF, UHF stuff, if you can afford it, LMR 400 is the way to go. It's a Times microwave product. It's the least loss at length for those frequencies. And when you go to purchase cable, usually every cable manufacturer will have a chart that shows this is what their loss is at 5 feet, 10 feet, 20 feet, 100 feet, so on and so forth.
A lot of them are just by the foot.
Yep.
So that you just do math.
Yeah, like it might be 0.3 dB a foot. So you do that calculation for how long you have there. The electrical difference between RG58 and RG213 coaxial cable is that RG213 cable has less loss at a given frequency. So that RG213 is similar to what LMR 400 is. You can tell it's a thicker, heavier cable. It's got a larger center conductor, it's got more of an insulator, it's got better shielding than that RJ58.
Just remember, the bigger the number, the better the cable. So 220, 213 is bigger than 58, so it's
Yep.
better. 400 is better, it's bigger, even bigger than
Yep.
220, so it's even better. So if you can just remember, typically, there's some nuances in there.
Which is weird though, because when you go to like LMR 600, 600, it's like this stuff.
Yeah.
But it's also less loss than LMR 400. Figure that one out.
But for the exam,
Yeah. Yep. At VHF and UHF frequencies, air-insulated hardline has the lowest loss characteristics. I don't think you're going to see hardline too often. That's normally repeaters. Actually, I do have hardline on my tower. And it's receive only too. It's just for receive only. Moisture contamination causes failure of coax cables. Yeah, I've dealt with that personally. Fiberglass antennas that leak, yeah, they don't last very long. A disadvantage of air core coaxial cable as compared to foam or solid dielectric types is that it requires special techniques to prevent moisture in the cable. I'm surprised they put that on the technician. You're not going to get into hard line. The outer jacket of coaxial cable should be resistant to ultraviolet light because it can damage the jacket and allow water to enter the cable.
Sometimes a cable like that, LMR 400, will have a U after it.
Yep.
And the U signifies it's suitable for underground.
Okay.
So just be a little careful about if you're putting an antenna outside, to not bury it unless there's a U after, and they all kind of take that same format. So you can get a Lot 58U or a 8X, RG8X, I've got some 8X. So,
So, yep, these are the connectors there. SMA and BNC, doesn't look like that's on the test at all. The N connector is the most suitable for frequencies above 400 megahertz. It has the lowest loss in that area. The PL259 connector is commonly used at HF and VHF frequencies. I do still prefer N connectors for VHF.
More professional stuff.
Yep. When you start getting into, if you ever purchase like a commercial, like a Motorola radio or something like that, it will come 9 times out of 10 with an N connector or a mini UHF.
you'll have to know that. So there's an N connector. I think this is N on one side anyway.
Yeah, the rig blasters and
Yeah, so there's an N connector, and there's a 259.
Okay.
So, I mean, there's a picture of them up there, but, so here's, the 259 is the plug, the 239 is the receptacle, and then that's an N that I'm handing around as that sort of extra ring around it.
that's what I had to go fix at the sheriff's department today. It was an N connector. A loose connection in an antenna or feed line can cause erratic changes in SWR readings. So if you get, especially if you're sitting at your base station radio and signals are coming in and out, check your connectors first. 9 times out of 10, they're loose and they're wobbling around in there and they're creating high SWR or they're coming disconnected altogether. Tight connections are very important. And that is the end of that one. Yeah. So now we're moving on to what are some practical ways to erect antennas. Yeah, I see that. Working all day on installing my clothesline. I was going to say, kick on that kilowatt amplifier and speed up that drying process. Oh, jeez.
That's Mike.
One of the things you'll get to do getting into this hobby is you'll have the opportunity to go to Hamfests and swaps. And Dayton, Ohio is like the biggest in the nation. And you show up at Dayton, Ohio for the Hamfest and you will see all of this, all the time, all over the place. There's one guy that drives a Prius, and it's nicknamed Porcupine because he has like 50 different antennas on this Prius. And it is just, every single one of them radios has high SWR because look at how close together they all are. I'm here to tell you.
So they're all reacting with one another.
Right.
Which you don't want. I think that's it, Adam.
That is it. Any questions on any of that stuff? Okay.